Up. All right. So that works out. Cool. Thank you for everyone that took part in the great projector fiasco of 2024. Let's finish this class before we get the next hurricane. All right.
Not maintaining.
Not telling OSHA.
So far we've talked about, most of the things we've talked about anyway had to do with static types, right? We saw a couple of different examples of types that weren't statically typed, or weren't concretely typed. They were generics, but we didn't know them by their real name. And today we're going to learn them by their real name. We've got to stop the conversation there. So we have this thing like result TE would be one example of that. In this case, we don't know what the T and the E stand for, right? This is an example of a generic that we've seen, but we never actually called it by its name, a generic. And the reason why we didn't do that is because it requires a little bit more to understand and a little bit more to grok this concept, and it's easier to just run over it when we're talking about how Rust does error handling. Now we're going to explain what the magic sauce is, right? So when we have this, when we say over here, result TE, that is telling Rust that we have a type, this result type, right? But it's not a concrete type. We don't know what success and error are represented by until that type is used, right? So result TE can be any type of success or any type of error, right? And now we're going to see how we kind of use this concept in Rust to remove code duplication and to make the functions that we write operate over different types. So when we do this, we see this concept in Rust quite frequently where we implement a trait, right? And these traits do things that we've already seen. One of the traits that we've used is display and debug, right? When we want to print something out, we know that what we're telling that thing we want to print out is display yourself. When we want to see what that thing looks like so we can make sense of how it's internally represented, we tell it, we want you to debug yourself. We want you to print out something that is about your internal structure. These two traits, display and debug, get applied to different types. And what print cares about is that whatever you give it has the ability to display itself, right? So in this sense, you could say that print doesn't care about the type of the argument you give it. It only cares that the argument you give it implements display. This is where this functionality comes in handy, right? If we didn't care at all about the type, then we would have a system that was untyped. Rust allows us to say, we need a type that implements this trait. And if we don't have that component, we can't make any assumptions about the type. So when I say I need a type that implements display, I don't know anything about that type other than the fact that it's implementing that trait. I can only do what that trait tells me I can do. That's an important distinction. There's a lot of things a type can do, but when you don't call it by its name and you call it by its trait, you can only do the things that that trait implements, right? And now we're going to see how this makes the language more useful than it would otherwise be, right? So here's an example. We have this thing, a number list, and we're creating it with 5 different numbers, 34, 50, 25, 165, and we're saying the largest number is largest. This is a piece of code that's going to pick out the largest number in that list, right? And here is the example of the code underneath. So we know that we have to be able to iterate over that list, right? This is the iterate trait. And we talked about this before. If something can produce a next, right? If it implements this iterator, we can effectively loop over it in Rust. And this is how we loop over everything. That thing we're looping over implements the straight iterator. The for construct doesn't only work on one type. In some languages it does. An example of this in Perl. In Perl, when you say I want to iterate over an array, for works with arrays. For says this is an array, this is what I expect, I'll work with it. But if you want to iterate over something else, like an object, Perl doesn't tell that object, how do I iterate over you? There's no language back and forth like that. For in Perl is effectively looking for an array, something that can act like an array. Then it's saying, I'm going to process you as if this was an array. In Rust, there's this behavior behind the back end. For doesn't care what it receives. It doesn't care if it receives an array. Doesn't care if it receives a struct. You are telling that thing how to behave in this context with this trait. So we have this first trait that we know is implemented on the number list, right? That's that iteration component. And then we know that as we iterate over that number list, we're going to take a number and we're going to compare it to something else, right? So I can tell you from this code here that for has to iterate over something that's iterable, and every different thing you're iterating on, every different element in that iteration has to implement comparison, right? And that's what we're going to see. We're going to see when you start to think of things like this, we can make a function that abstracts this code out, but it doesn't just compare numbers. It could compare your own objects. If you have, for instance, vehicles or people, you want to compare people by weight or height or whatever, is the metric we're putting people up into. You can say, how do I compare one person to another person? And if you say I want to compare them by weight, we're going to implement a comparison mechanism for people that looks at the weight. Then I can say person A greater sign person B. The comparison sign will say, how do I compare these two? The thing will say by weight, by height, and you'll be done. So we'll see that. And to talk about how we're going to do that, let's actually see something here. Let's get rid of this. Boom. I have this one already ready to go. OK, I'm going to do RS, and we're going to go down here to CMP. And I'm going to show you how this actually looks now. Utilities, so I just typed in CMP, right? Because I happen to know that this will get me at least close enough to where I want to be that I can figure this out. So right away, ordering is an enum returned by the main functions of ord and partial ord. So this is the result of the comparison. Here we go. Define total and partial ordering between values respectively. Implementing them overloads these operators, right? So this is what I want. I want ord. So this is what I need, right? So this trait here is what's required to make the comparison operator work. And we're going to see how that looks. This public trait ord, it requires us to implement comparison. That's the only thing that's required. We can provide these, but we only need comparison. I'm showing you this to show you this is a way where we can implement this comparison on our type. And then in certain contexts, I can say, you need only tell me that I can compare these two things, that I implement this. Then I don't care anything more about it because I can call CMP on it, which is what your greater than and less than signs are using, right? So here, this is telling me that number is implementing compare. It's going to come over here. It's going to use compare, which is going to take self and a reference to the other thing, which is of the same type. So that's what the syntax means. Of course, we've already seen this one right here. We've already seen this. This means that we're going to take by reference, borrow a copy of self, that's read-only, and then we're going to do the same thing, but the other side of it, the other thing we're comparing it to has to be of the same type, right? So that's how comparison works. So number and largest, they have to be of the same type. That's how we implement it. It's implemented on the number type. And again, we're iterating it through, and we're saying, can we compare these two things? So here's another one we have here. And this time, we're showing you we want to run the same code twice, and now we have two different number lists, right? So now we're seeing this, and we see this code duplication. And what the book is trying to do is the opposite of what I'm trying to do. I'm trying to bring something else of value to it. The book is trying to show you these generics as in just the method of reducing code, right? And that is, there's definitely a degree of truth to it. It's one way you can look at generic functionality. It's not the only way you can look at it. It's not just simply code reduction. It's a lot of power there too that has nothing to do with code reduction. It just makes more sense. But if you ever see something like this emerge as a programmer, right, the book is right to say you should start to ask, how can I do less of this? This is a pattern. I see it. We're just trying to find the largest number in a list. So you're going to take it out. You're going to try to put it in a function, and that's totally fine. Here's a function that'll do it. This function takes a list of I32s, right? Essentially, we're looking here at now having this list of I32s, and what we're going to return is one of them, right? So just reading that type signature, we can tell a lot. We're taking a list of something and we're returning one thing in it. What is that? What possible things could implement that? Largest could do that, follow the type signature. Smallest could do that. First could do that. Last could do that. Middle could do that. Those are all different functions that could have that type signature. I don't think you're going to find many others, right? So I'm saying just by looking at that type signature, I've seen that so many times, I can already predict the implementation to be one of those few things. You start to look at the type signatures and they tell you, they speak to you in a different language, you know? They really collapse down what type of code you could be looking at. It is definitely a different way of communicating. And you get really good at it. We can actually do some examples where I show you some of the different ways we can think about this. But here we have a number list, and now we're calling largest on it. And then we have a second number list, and we're calling largest on it. This works. We've reduced the amount of code to one instance of this comparison function that's just finding out largest. The problem with this is we're stuck now on I32s. Suddenly, if I give it an I64, that implementation doesn't work. And that's one way where we could think generics come in and they save the day, right? All right. So here is an example now, and we have, this is a horrible pattern, right? This is a horrible pattern because we are including a type name in a function. Now, this is where I would say the book is somewhat short-sighted in the way they're presenting it to you. Because I could take one of these and say, regardless, it's wrong. Let's say you're never going to compare character at all. Even if you're never going to compare character, it's wrong to have a function that's typed to I32s like that. It's just not the right way to do something. It's prohibiting you from using that function elsewhere for something that may be useful on, right? So that's kind of the way that I like to see it. I like to see this as a piece of functionality that's not just about code reduction, though it does that too. But a lot of times you're writing code and you want to, why would I want to write that code that was specific to just the 32-bit integer? It's not right, even if that's only the thing you're comparing. That's my opinion on it. And by the way, not just is it not right to do it like that, I would also go so far as to say it's not beneficial to do it like that. The way Rust works with generics, it will actually generate for you a function for every different type you use it on. You don't see any of that. That's the way generics are implemented in Rust. That means you don't pay any runtime performance costs for it. And if you only ever use it on one type, you only have one function generated. So Rust conceals all of those details to you, and it's really nice. In other languages, sometimes when you use generics, things get slower because it has to make these decisions in runtime. Which implementation do I use? How do I compare this type versus the other type? Rust does not. Rust will generate a different copy of that function for every different type you need it on, and it'll only do that if you ever use it. That's the language of the Rust compiler, right? So now we have these two different types, I32 and character, and we have these two different arrays here. We're creating a vec of the top and a vec of the bottom, but now we have this ugly nonsense, which is not what you want, you know? I don't want to have to look up in the documentation, you know, what function I need because you implemented it for I32 and you called it largest integer or something like that. You know, I want to be able to just say largest. It's a shorter name. It's better. All right. And here's our solution. Our solution is we change the type a little bit. Now we introduce this thing called T. And this will blow some people's heads. And if it blows yours, it's totally fine. If you've never seen the syntax before, it's not going to sink in right away. It's totally normal, right? And the reason is it's effectively a higher ordered function type. And anytime you hear the word higher ordered, if it's your first time seeing it, it's going to suck. Totally normal, right? Higher ordered function is a function that takes another function. If you've never seen a function that takes another function, the first time you see it, it's going to suck. Because now you're getting a function as an argument. The same thing is true about a higher order type. The first time you see this and it takes a type as an argument, it's going to suck. You're going to have to wrap your head around it, right? So now we have effectively this thing here for a slice. We're going to take this list here, and we don't know what that is. And here's the thing. You will never know what that is, right? Because we're not speaking about it in a concrete type. Only after you compile that code do you know what that is. Because again, if Rust doesn't need it, it doesn't make it. And how many copies does it make every time it's used? One potential copy every time you use of that function. So if you use it on 50,000 different types, you could make your code slightly bigger. And there's an area where this actually comes into play, and you do have a ballooning effect. But it's not something we worry about too often. So yes, in this case, we know that we're receiving many things in this list, and we know we're returning one of those things, right? And now we no longer specify what it is. We would say that this is a generic type, and we are returning a generic type. This is of type T. All right, so now they're telling us here that this doesn't work. And the reason why this doesn't work is very clear to me. The reason why this doesn't work is because we're telling it inside for each item in list, we need to know that we can compare item and largest, right? So we're saying that you can have a list. Here's why you have to do this. You can have a list of things that cannot be compared. You can have a list of things that can be compared. You have to learn to speak the language of the compiler, which is if you're going to be comparing things, you need to narrow down that list that you're taking to things that can be compared. And there is a special grammar for that. It's called trait binding. And we'll see that in a bit. Here's what it looks like when you screw this up. And by the way, this looks less and less intimidating every time you see it for at least the first year. And eventually, you'll get there. We see this thing, item is greater than largest. And we see both of these is a type T. And it says consider restricting the type parameter T. And it tells us right there. Here's the thing. I didn't pre-read this chapter. Had I pre-read this chapter, I would not have looked at ORD with you. I would have looked at partial ORD with you. To tell you the truth, I don't exactly remember the difference between ORD and partial ORD. And I guarantee you I've asked that question before because I remember having this problem before. So I bet if we go to Google and we type in something like partial ORD, Evan Carroll. Here, does Rust allow you to define ORD or partial ORD on your type and external types? You know, I've had this problem. I've had similar problems with this before. I know that I've had these things that have popped up before. And people have helped me on just this very type of thing, right? And the deal here is, if I recall right, I think this returns an ordering, ORD returns a concrete ordering, and I think partial ORD has a way of representing that two types can't be compared. Let's see here. CMP, we have partial EC, that's how that's pronounced, partial EC, partial equality, partial ORD, partial ordinality, and here. Yeah. So partial ORD, if we look at it, we have this partial CMP that it implements. And partial CMP returns an option of ordering. So why is that substantial? Because if you have a type and you don't know if you can compare it, you can implement partial ordering. And you can still use greater than or less than. Now, here is the bonus point question. What is the canonical example of types that can't be compared? Always one of them comes up. No. Yes, float. Floats cannot be compared with each other all the time because floats implement bullshit components called nan, right? So if you come from the JavaScript world and you've ever seen nan, not a number, this is effectively, it is a float, but it is a float representing a type that can't be compared with another float. Anyway, when you have this problem, every computer in the silicon has a chipset that is designed to handle floats. These numbers that aren't real numbers, they have a fractional component and a solid component to them. I forget. I hate math terms. One of them is a mantissa. The other one is another stupid math term. Get a float guy and a math. You're a math guy? Exponent, mantissa, and exponent. That's how it goes. So one of them has got all of the decimals in it. Another one tells you where you're supposed to put the decimal. That's how it's represented internally. But the point that I'm making here is that this is built into the actual silicon. So it sucks, and we can't do anything about it. And it's been with us for 30 years, and no one has a better solution for it. So this whole thing about partial ORD is all done to build around that, right? This is how we can represent floats in a type-safe fashion. You can't compare all floats with each other. Some floats, when you compare them with each other, like if you compare a number float with another number float, you will get none with partial order. So that's why that exists. So it's coming over here and it's telling you, consider restricting the type. You need to specify partial ORD. Partial ORD is a less restrictive qualifier than the one we were looking at earlier, which is ORD, because it allows you to have some of those types that can't be compared. They'll just return none. Okay. Yeah. I just wanted to explain that. It's not entirely relevant, but yeah. Does anyone have any questions about this idea of restricting the type to partial order? Yes.
So when you institute this, obviously there are some parameters that can't be passed, right?
Yes, yeah.
When does that get flagged? Like during
Compilation.
Yeah.
Compilation. Compilation, when you try to pass something that cannot be compared at all, that doesn't implement partial OR, it'll come up to you and say, these two types can't be compared. Therefore, how can I ever determine what is the largest? Doesn't make sense. You know, function largest requires, and that's true. By the very notion that you have a function called largest, you have to be able to pick out which one is larger. You know, if you're giving me a list of types that a list of a type that can't be compared, how am I ever going to decide which one is the largest in that type? I'm not. So we have a problem. And that's a type error, right? That's where Rust is very handy. The type system will save you from this kind of stuff.
In SQL, it just ignores it.
In the best case, unless you're using MySQL, in which case it's fully insane. Yes. Cool. Does anyone have any questions on that? No. I guarantee you there's a lot of people that haven't wrapped their head around it, and it'll come though. It's not so bad. It's bad enough to where a lot of people have to look at it multiple times. So here now we have the struct called point t. This is nice because this is very simple. This takes an x and a y, and they're both of the same type, right? So this generally works. And what I mean is we have a very simple type. We're saying that both the x and the y coordinates are of the same type. That works really well in this x and y format. In other examples, which we will see, like for example, result, the thing that you return when you are successful and the thing that you return when you are in error are two different types. So in result, your t and your e are different types. We could have defined result to have result t comma t. Then we would just simply have to return the same type on success and on result. Does that make sense? Here, we're taking a point of t, and we're saying both the x and the y have the same type. So the generic system can have multiple variables. Result is a case where we have two different variables, because we are representing two different potential types, the result type and the error type. In point, we have one type variable t, which means that x and the y have to be the same type. Oh, I just jumped all over the place. There we go. All right. Now we're over here, and we're showing you why this won't work. We know right away why this won't work. X is 5, right? And y is 4.0. Y is a float. X is not a float. So we know we have two different types. Our point requires the x and the y to be of the same type. Therefore, you will get a typing error. That typing error will tell you very simple. Mismatch type, expected integer, found floating point number. Why does it expect an integer for the second type? Because it knows what the first type is, and it knows the second type must be the same. Rust doesn't just tell you, you have to provide two of the same types. It's saying, in this case, I can build a point out of any one type. But whatever that type is, you have to give me that type on this side too. So it's telling you exactly what has to be here to satisfy this concrete point. This point requires that second y to be a 4. And that's the word we would use for it. You have a generic notion of a point with one generic type variable, t, and then we have a concrete point, which is a point of integer. This is saying, I won't work because I am a point of integer as determined by this. This is what determined my type. Therefore, the y must also be an integer. OK? So when we have that one type variable, both integer will work, both float will work, integer and float will not work. But if we come up here and we change that y to a type of u, suddenly they'll all work. Because now I have said point can have two different types, one for the x and one for the y. And this is how result is implemented. Result is implemented when we see result t comma e, it's implemented just like that. Very similar anyway, you know? It's implemented like that because we're telling you that both the OK and the error type can be different types. Just like we're saying right here, both the x and the y, both is not the right word, the x and the y can be of different types. We have two different type variables. We're assigning one to each. All right. Enum, there we go. Now, I said it wasn't exactly defined that way. The reason why it's not exactly defined that way is because result is an enumeration. And we were just looking at a struct. So now we're actually going to see the exact implementation of result. Struct effectively has one way to construct it, right? You provide it the values that are needed. And an enumeration has two different constructors for that type. So now I have this type called option. And what we should see from that is we have a sum t and a none. And that's the option type. Now here's the thing. Are all nuns the same? No, they're not all the same. But you can generally get from one none type to another none type. So there is a method in which you can do that, right? So they can be different, right? Down here we have this result of t and e. And we have the same type of thing. We have the OK t and error e. This is one I've been talking about extensively. This works because they're both different types. So you can return whatever you want on either side of it, and it'll figure it out. And that's another way to think about that, right? When we have two type variables and they're only used in one place, what you're telling Rust is effectively make this work if you can. If at all possible, make this work if you can. Why? Because there is no trait bounds on either one of those two types. So I'm not saying limit what you can take. And I'm saying it's only used in one place, so anything can fill it. That is a maximally inclusive method of having a result. Anything can be included for the OK side. Anything can work for the error side. There are no limitations on you. And they're only used in one place, so I'm not even saying you have to use it in both places. Any questions? OK. So now we have this point, we're recreating it. We have an x and a y, and they're both of type t. We've already talked about the shortcomings of it. Now we're going to implement a trait on that, right? Now this isn't actually a trait implementation. This is just implementing methods, right? So I take that back. We're implementing methods on that. Now this is, in my opinion, a very weird syntax, right? Because we have the two t's. We have the one t here, and we have the one t here. That is a Rust thing. I don't know why they did that. I'll be honest, I don't know why. You just get used to it. You just figure it out and you get used to it. You say, OK, I just got to reproduce the typing variables on one side on the other side. And I haven't figured it out, because other languages don't do that. Other languages may just put it on the point, t. I'm sure there's a reason, and I'm sure it comes from some real dweeb in math. But in computer languages, they do it both ways. So we get to shit on the dweeb in math, and then I just, honest with you, I don't know why. So this is the right syntax, though. You must list all of the variables that you're going to use on the impl, and then you can use them in different places here, right? So but if you have it here, it must be on the impl. But Rust can't figure that out. All the things Rust can do, that's going too far. So if you have things on the impl, you can also use them in other locations. Like here we have this one, right? So the impl must have the entire list of types, and Rust will not infer it. You must give it all of the different type variables you want to use. So we are implementing one method called x, and it says, given a reference to self, I will return t for whatever that t is. Right? We only have one type variable in this because the point itself only has one type variable. So it doesn't make sense to have an impl with two type variables because the point only has one. That's not entirely, yeah, it's probably not entirely true, but it's true enough for now. We can go over some examples where that's not true later, I guess. But here we have this one, and we say let p equals 0.5 and 10, and then we are printing out p of x right here, so p.x. Now this is going to, this is not code, this is just a string, right? So how are we accessing the x? We're accessing the x by using the method x, right? That is what we implemented above. So we're showing you how to write a custom accessor to that data you've got, right? And this follows the same logic too you see in object-oriented programming languages, right? If you ever use an object-oriented programming language, some of them give you the ability to mutate the data internally, like Python, like Perl, like Ruby. You're not supposed to do that. You're supposed to go through a getter method or an accessor. Same thing is true here. You're supposed to give your users an ability to access your internal data. You're not supposed to let them disassemble your struct and figure out where everything is at. Because if you do that and you ever change your internal representation, you're going to have a lot of people pissed off at you. if you give them a controlled interface and you change your internal representation, so long as they get the same thing out of it, they're going to be fine. Okay, distance from origin. So now we have an implementation on point, and now here's the key. This function, distance from origin, is only implemented on one type of point. We would say it's implemented on the concrete type of point of F32, right? So there's one instance in which point is constructed with an F32. Only on that point do you have this function. On all of the other instances of point, you don't have that function. So even though the point itself can be generic, you can implement a function on one thing on it. See? And this is what they're saying right here. This is what we just got to. All other instances don't have that functionality. Okay. Now we have point, and again, we're still running with this example, and we have two type variables on it, but rather than giving them one letter, we've now given them one letter and one number, x1 and y1, right? The convention in Rust is almost never to do this. Almost all types are one letter. Math, I don't know, blame it on them. That's just how people tend to write things. But down here, we're implementing x1 and y1, and we have this point, x1 and y1, and we're doing this mix-up, right? So we have effectively, we're taking our self, which is the struct of the point above, and we're taking another point, right? And we are swapping them. So we are returning we're returning a point that has the x self x, y other y. So we're taking the x from the first one, and we're taking the y from the other one. That makes sense. So we have this thing mix up. Mix up takes another point, and it only ever looks at your x and their y, right? So if we have two different points, and they have, let's say that, here, let's look at this. Let's actually run this. Probably be easier. Cargo, new, bin, point, boom. Okay. So, what we're looking at here well, that is annoying. It's just chopping out. OK, I won't save it. There we go. What we're looking at here is the, let me make it, I guess, a little bit bigger. Enhance. There we go. All right, we have this P1, which is equal to x5, y10.4. And we have P2, which equals x hello, yc. You're going to notice that in the top, we have x is an integer, y is a float. In the bottom, we have x is a string, y is a character, right? More aptly, x is a string slice. And then we're saying here, mix up, p1.mixup p2. So we're mixing up this one and this one. That's going to mean that p3 is going to get the x here of 5, and it's going to get the y of c. That's what mixup is doing. So we're taking this value here and this value, and we're constructing another point of that, right? Now the key here is, and I said this earlier, when we have a point and we use that type variable only once, and we don't specify trait bounds on it, we're telling Rust to be maximally inclusive, right? This is an example demonstrating that. Rust has no idea what your intention is here, but it's going to make it work. And the reason why is because this can be anything and this can be anything, and we have a point type that'll support anything in either one of those positions. So because that is the case, this will work. And we can go ahead and run this code, and we should see x5, yc. And then there's our example. x5yc down there. Let me clear that. There we go. Now we can see it up there at the top. All right. Performance of code using generics. This is just what I said. This is a big word that I think that was stolen from C++. I don't know, it may predate it. But monomorphization is the concept that we will, from this generic code, create concrete code. The concrete code only works with one type, as if you wrote code for only one type. But it's generated for you at compile time. And the key here is that that concrete code is maximally fast, right? It has no overhead of this generic abstraction. That's what you want. Rust has another method of having overhead for generic abstractions for things that look like generics. But in this case, when we use these type variables, right, these generic type variables, that code gets monomorphized. Monomorphized. That's the one I've never used before. It goes through monomorphization, and you get this concrete code. OK, so here's an example of an option. This time we're doing I32. We have another option of F64. And we are creating this integer and float from these two different discrete option types. And what they're saying here is that the generic option T is replaced with these specific definitions by the compiler. So what they're saying is, we have only ever seen option T, which means that you can create it with some. That's what option means, right? We construct an option using some and a type, or value, or none, right? What Rust is showing you is that option T is the same as if this was written by hand. Given these two implementations, I32 where we're giving it an integer, or F64 where we're giving it a floating point number, right? That option T is the same as this. This is what the compiler does. It writes this code for you. You just don't see it. OK. So now we get to this area of, OK, we have this generic code. We have this ability to write generics. How do we make it useful? Right? When I said that this is an implementation of a type that is maximally useful, that doesn't mean you can do anything with it. It just means you can store anything inside of it. Now the question is, we want to do something useful with it. We want to compare the things inside of it. Now we're going to see how we can do that. We have to constrict what we can receive by these traits. And now you're going to see how we can do that. Here we have a public trait called summary, and it implements summarize and returns a string, right? So if I take this trait that was created, summary, if I implement on 10 different types summarize, now I can suddenly do something useful. I can say accept anything that implements summary, and I can only do one thing with that now. I can call summarize on it, but it's something. I have a behavior that I can do now on 10 different types if I implement my trait on 10 different types. And that's kind of how Rust builds up as a system. So here is a type. We call it news article. And it has, in this struct, news article, we have 4 different fields. We have headline, location, author, and content. And we are implementing this summary for the news article. And here's what it does. It's just going to summarize our news article for us. We have another struct called a tweet. It has 4 different fields. And we're implementing a summary for a tweet. Now I can receive tweets and news articles, and I can only do one thing on them. I can call summary. So long as I say, accept any type that implements summary, I'll be able to do anything that summary implements. Now let's talk about one other thing here before we hit on this. Let's talk about this notion of accepting a type that implements summary. What if I need to be able to compare them to?
We would have to implement compare.
Have to implement compare, which is true, but you'd have to restrict that function to accepting types that implement both summary and compare. So now a function would be able to compare them, pick out the largest, and then call summary on it. You have 2 discrete pieces of functionality. Comparison is in one trait, and summarize is your own custom trait. And if you need to be able to do both of them, you need to say that the types I can receive are constricted by both of these two things. I think it's constricted. I always get that. Constrict stops something from blowing out. Restrict pulls it in. Constrained. Yeah, that's better. Constrained. Constrict is what a snake does, which is the same thing as constraint. I don't know. Anyway, what was the question?
I knew where you were going with that, where you add multiple traits, and I was just going to chime in with that, but you ended up saying it, so better than I would.
Yeah, if you have anything you want to add.
I do have a general question about Rust though. You know, there are some languages that do result in a compiled binary, where there's an interpreter that allows you to have an interactive debugger as you're going. So at any point you can see the values of different variables and whatnot. Is there any? It looks like with Rust there's no such thing, right? There's no way to.
You can debug Rust.
You can debug Rust, yeah. Yeah. Rust has, now debugging in Rust tends to be substantially less useful than a lot of these other interpreted languages because you know far less about the type, right, that information when you're running the debugger because you're actually looking at it at a lower level. Like when you run Python code or Perl code, you have a lot of information about what you're calling it on. You know, you have the linkage to the object is there. When you compile Rust code down, you can compile it down to a level in which you lose all that information. You're running it at the fastest possible speed.
Right.
So a lot of the other languages you're talking about don't have a notion of losing that information. They just wouldn't work. Whereas Rust can lose a lot of that information. So you can debug Rust, but you will not get the same quality of information you would get in some other languages that you may be used to. You know? It's got a very good system for debugging now, but it's not. Yeah.
Can you go back up to the where you said where it's let P1 equal point x5 and y10?
Yeah. Can I just go to the code, or is this the one you're talking about?
Sure. Why does so P1 dot mix up P2? So P1 is imposing its data on P2. Whenever it prints the line, why doesn't y print out 10.4? Why does it print out C? Like, why does it print out what it prints? Like,
Because
I don't
it takes
understand
P2 as
that.
an argument.
So what it's printing, just so we can go back and see it, P3.x is 5, P3.y is C, right? So P3.x is 5, P3.y is C. Why does it take the first element from self and the second element from the argument?
Yeah.
That's your question.
Yeah.
And the answer is very simple to that. That's because that's how it's defined. Here's the definition. This is mix up. It is typed to take two different things, self and other. Other is a point of x2, y2, right? So look at down here. We're implementing it on a point of x1, y1, but mix up as a function has its own two type variables, x2, y2. That's what other is typed to. And it is going to return a type of point, which is typed to x1, which is the x1 is up here of the self, and y2, not y1, y2. y2 is the y value that you were giving it in other.
In my defense, I didn't know that mix up was a function. I thought it was like separate.
Gotcha. Yeah, no, this is the thing that we implemented. Then it's always good to ask, because you can, and if you have any further questions, definitely ask them.
So the type definitions of mix-up follows the same logic as the ones on implement, where like if I had other two with x3, y3, then you have to have mix-up x2, y2, x3, y3. Like does it have to have everything?
Well, if you,
define
yes.
x2, y2 twice again, like you do with implement.
Yes, because you always, yes. So the question is, whenever you're implementing a generic on a function, you always specify the type variables after that function name, mix-up. These are the type variables here that the function will use, right? We're implementing it on a struct, and these are the type variables for the struct. So this is the method on the struct, has its own two type variables. But The method, yes, the method on the struct takes an argument, which requires 2 type variables. The implementation on the struct, right, is reflecting the struct itself, which has 2 type variables. So we're saying implement on point, which has 2 type variables, mixup, which takes other, which has 2 type variables. So other is typed not to the struct you're implementing this on, but it's typed to an argument. And I'm saying that argument can be 2 different type variables. So we have 4 potential type variables. We have the 2 on the struct we're implementing mixup on, and then we have the 2 that are provided to mixup in the other argument.
On the mix-up, do you have to put it in the same order as your arguments, or does it not matter?
The same order as your arguments. What do you mean by that? Like you could take it and you could say this. Let me see if this makes more sense to you. We could say here, rather than x2, y2, right, we could say f, z. And then I could say here, f, z. And then I could say over here, z. That would work fine.
But could you say mix up z, f, or does it have the same?
I could, but I have to change all of them. So if I want to do here, mix up zf,
Oh, it has to be the same order.
well, this order here, right, has to define what you're returning. So point that I'm receiving is type 2 f of z. If I want to switch these, right, I could do that. I could say point z of f here. Now I know this needs to return f. This would also work.
Remain the same. That.
He's
My
asking
question
about the
is
function
specifically
definition
about
typing,
on
not
mix-up.
the argument.
Your question is specifically, I'm sorry, I may not be getting the question.
He's asking about the
Is that
function
what,
definition typing,
as it is,
not the
it would
argument.
run, it would compile?
This would compile, yes.
Okay, that was my.
Yeah, this will compile. And we can give it a shot here, just to make sure.
And you left the z.
Oh, there we go. Yep,
You can, but everyone on the internet will be able to hear.
yeah. You can definitely, by the way, that's also a valid point. Why don't we do this? Because that's insane. I'm just showing you that you could do it, right? So your question was, can you do it? The answer is yes. Should you ever use the type variables that are declared out of order? No. If you declare the type variables A, B, and C, you should use them in the order, or at least as close to that order as possible when you're using them in code. You shouldn't just switch them around, because that is definitely going to be a what the fuck moment for whoever's reading that code, right? But it'll work, you know, and that was your question. There's nothing in the language that stops you from doing that. All right. Okay, so now we have this summary type, and we have it on a tweet. So here's this tweet we have. It has username, content, reply, and retweet. And I'm calling now tweet.summarize, and this is going to work. OK, so now we have a default implementation. I'm going to go to drink. I'll be right back. Default implementation will work on anything that implements summary, right? That'll be the default, which is very simple. Oh, there we go. OK, that's better. All right, so this is sometimes called a blanket implementation. And what this means is that we are, actually this is not called a blanket implementation. Let's just call it a default implementation. I think a blanket implementation is technically something different. So this default implementation, anytime I implement trait on something, if I choose not to provide an implementation of summarize, that's the implementation we get. It is something. Now I can just say IMPL summary for type. And that's what I'll have. You can implement it on all of the types, and you'll have that kind of thing. Which is not actually totally bad, because let's say that you're doing comparison, and you want to pick out the largest one, and then you're calling summarize, and it doesn't make sense to summarize it. You may be able to take a list, and I see the largest one. Maybe the largest one doesn't make sense to summarize it. So I just say, you know, rather than summarizing it, it's the Bible. God said no. there's your, you could do something like that, and then just have this scrap implementation that works for everything else. All right, we have news article. Article has all of these different fields here, and then I call article.summarize, and now we have new article available. Why? Because new article doesn't have a custom implementation of summarize. It was implemented using IMPL summary for news article, right? So if we wanted to provide a custom implementation, we'd say IMPL summary for news article, and then in this, we would specify our implementation. I would say function summarize, and I could do something intelligent. But if I choose not to do something intelligent, it'll just use the default. Now we have an implement summary for tweet, and now what I have is we're redefining summary. That's what I didn't catch. We're now redefining summary to where we have a summarize and author, and we have summarize, right? So we have the summarize down here actually looking up the author's name. This is sometimes useful, right? And the reason why this is useful is we can implement a custom summary, right, with just specifying the author, and we can have the summarize function dynamically change in a blanket implementation. So we can do that kind of thing. We can implement half of it and have the other half of it work, right? If we have two different defaults and we override one of them, we could change the other default. And this is what they're trying to show you here. So now we implement summary for tweet. We give it a different summarize. We give it a custom implementation of summarize author. And now, because it's a tweet, we prefix it with the ampersand, because you're not an author on Twitter unless you start with an ampersand. OK. And then this is what this looks like. One new tweet, read more from Horse eBooks. And that works, right? So we see down here, when we implement it, we implement a custom summarize author, but we rely on the blanket implementation, the default implementation for summarize. And it does the rest, right? The whole entire read more from, that's the blanket, the default implementation. And then at Horse eBooks, we're getting this component from the default implementation because we are providing it a custom username. So we're saying, this is the username. You generate summarize username by looking at that. And then we use that to generate the default implementation of summarize, in the default implementation of summarize. All right. So let's check here what our progress is in our time. There we go. What is that there? OK, we have one more section after this. One more part of the book.
I think we could do chapter 10 this week, next week, and the following week.
Oh, you want to just keep juicing chapter 10?
Let's do chapter 10.
Yeah.
Until we could get my head wrapped around all of it.
All right. So shared behavior. Traits as parameters. OK. Now we're going to talk about how to implement. We talked about receiving a type that is maximally useful, provides you no utility, right? A type that can be any type that can be fulfilled by anything doesn't mean you can do anything with it. In fact, a type that can be fulfilled by anything means you can do nothing with it. There you go. That's your takeaway. If I create a function that can receive any type in Rust, you can do nothing with it. So what do? If you want to be able to do something with it, you have to tell Rust what that something is you want to do. And here's what we're doing. I'm saying public function notify takes an item. That item must implement summary. It's the only thing I'm saying. Now, because that item implements summary, what can I do that's useful? I can call summarize, right? And now suddenly I can make utility. I can get something done. Trait bound syntax. Now, this is new. Some people like this syntax up at the top. This is the one that I use down here. This is just the way my brain works. But by all means, do with your brain whatever you want. We specify the type T, and then I say that effectively colon, and I can list the names of the types that it's limited by. And there's some other advantages of the trait bound syntax.
Is Is it just kind of separated from multiple?
No, plus. If you want to do trait 1 bound and a trait 2 bound, it's trait 1 plus trait 2. So down here, we have a notify, and notify takes an item 1 which implements summary and item 2 that implements summary, right? Now, here's the catch on this, and it is not necessarily clear. This is telling you that they both must implement summary, but they could be of different types. That is too subtle for my liking. Some people like it. Down here, I'm saying I have one type that implements summary, and it must use for both item 1 and item 2. So if you want 2 types that can be used, where item 1 and item 2 could be of different types that implement summary, I would just say T:\summary, comma, T2:summary. And I would say item 1 is a reference to T1, item 2 is a reference to T2. That's how I would do it. Then it's very clear you take 2 different types, you take 1 type. The way at the top with the IMPL is more sugary. It's another syntax sugar that they created. Got a question?
No, T1, T2, that's not like valid, right? It should be T and U.
No, T1, T2 is valid.
Well, no, it's valid, but it's not like proper, right?
Yeah, you're right. But I mean, I'm trying to make it easier for people. Yeah, it's not conventional. Yeah. Not conventional, but it's valid. There we go. Specifying multiple trait bounds with a plus syntax. Public function notify item. Now we're taking an IMPL summary and display, and they're showing you here that this is what it looks like to constrain your type you're taking by 2 different roles. You must have both of those roles. And here's the other syntax that provides you the same method for doing it. Important to note, the syntax at the bottom is the one that is considered to have less sugar. I think it is both cleaner and it is shorter. So you will save yourself 1 character. Adds up, man. By the way, show of hands. Who thinks the one at the top is cleaner? Who thinks the one at the bottom is cleaner? Top? Anyone think the one at the top is cleaner? So we're all the bottom people, huh? Okay. I dig it.
I think the biggest benefit is when you have multiple types, because then you don't have to say implement multiple times.
Yeah. Yeah. There's definitely some benefits there, you know. All right. fn sum function. Now we're saying we have a type T and it implements display and clone, and a type U which implements clone and debug. And I'm taking T, which is of type T, and a U which is of type U, reference to U. And I'm returning an I32. And here's an example of that function, right? So, or here's a different way to write it. So here's another way that people will write this. So this is another one of those areas in which there is more sugar. They think this is clearer. I don't think this is clearer. I think the top is clearer. But again, it's all subjective. You do whatever you want. Rust doesn't really care. I think if you come from other languages that use generics, which are not nearly as popular as they are today, they wrote them up the top way. Yes?
With the top, can you separate it into multiple lines?
Technically, yes.
The argument
Should
of
use no.
Yeah, I think that's the right answer. Technically, yes.
Because I think the one on the bottom makes sense if you have a lot of things.
Yeah. I mean, I just like my type signatures to look like book volumes. You know? You read them from the first character to the last. No, there's definitely merit there. You know, like maybe the bottom makes more sense if you have to spread them apart on lines. You know, I see the bottom is more acceptable than this. You know, like this syntax I don't see really anywhere. I do see a lot of people use the bottom here, so that it makes sense to them.
For the bottom as well.
Yeah, I guess a lot of people prefer that too.
Where do you
Okay.
see it on that
It's
work
ease
or-
of use for boss.
What's up?
Where do you see it at work or in other people's projects?
Crates.io.
Huh?
Crates.io, when I write batches to other people's crates. Yeah.
It's more readable, right? Like,
Yeah. Yeah. OK, so we have this thing return summarizable. And what this is going to return is something that implements summary. So I'm saying here's a tweet, and the tweet is specified here. Now, this syntax is also kind of tricky, in my opinion, because it has to be able to know what the concrete type is in compile time. So this works because it knows in compile time that this is of type tweet that you're returning. But the one at the bottom doesn't work because it doesn't know what you're returning in compile time. That is a subtle difference there, and it can sting you. It's one that you probably will have to learn the hard way. But Rust will tell you about it when you do this the wrong way. That is to say, you must know what a type returns when you are compiling your code. You can't do something like this, where you have a switch statement that decides it, or an if-else. Okay? The whole premise behind Rust type inference means that everything has to have a known return type. Yes?
Can you return enumerators then?
Can you return enumerators?
Like,
You can return an enum.
Ye-
tweets and users.
Yes. Yeah. It's not an enumerator. It's an enumeration. Yes. You can return an enumeration or an enum. Remember that an enum is one type constructed multiple ways. So you always know the type if you're returning an enum. For instance, when you return a result, right, it is one type, result TE, regardless of whether or not you return OK or error. Does that make sense? OK, so now we have this other one called std format display, and now we're going to get down to making our type printable. This is going to be something you'll do pretty often, right? So we have this pair of t, which means that the x and the y are of the same type, and we are implementing new on it. So we want the ability to construct it with new, rather than to construct it by doing the type itself. And I want to put something out here. This self, to me, is super useful. I do this everywhere. This makes it 1,000 times easier to copy and paste code around. So when you say it like this, that it's returning self, it's going to look at what it's implementing this on. It's implementing this on pair of t. So self will resolve to that. The same thing over here. You don't have to say you want to create a pair. By the fact that you're using self and you're implementing it on pair, Rust will figure that out. So you will often see self as a return type for an impl. It means you want to return the same type you implemented it on. You'll see it often for a constructor. It means you want to construct the same type you've implemented it on. And the kicker here is that, of course, we're implementing display. And we're only implementing, we are implementing CMP display on something that implements display and partial ord. Right? So I'm saying if you have a pair of t where t implements display and partial ord, where t can be displayed and where t can be compared, then do this. CMP display will say if self x is greater than or equal to self y, the largest member is x. Otherwise, the largest member is y. So it's going to compare the x and the y together and print out your largest member, whatever that is. All right. Any more questions so far? Now, this is going to be the one that you'd probably rather me stretch over another class. We have a whole other hour, so I say we do it. Preventing dangling references with lifetimes. So it turns out, as if the whole generic thing wasn't confusing enough, that generic functionality is the same thing that is used to implement lifetimes. So now is when it becomes even more confusing. So far, all of the generic types we've seen represent a type argument. And I told you that before it gets compiled, Rust has to be able to say, I know what that type argument is. If Rust doesn't know what that type argument is when it gets compiled, Rust throws up its hand and says, we have a big error. We have to clarify this. We have to disambiguate. You can't compile this. You can't do it. OK, now we're getting to the area of lifetimes. And Rust does the same kind of work, in a sense, but different. When Rust is determining whether or not two types can exist when they have generic arguments, it has a method of resolving that. Right? It's a type solver that figures that out. Now we have these generic lifetimes. We're going to see the lifetime solver figure some of this stuff out. And what they're trying to do here is say that when we use lifetimes, we can kind of think of them like generics too. We don't know concrete lifetimes ever. we never tell Rust this value is good only between lines 100 and 105. We don't tell Rust that because Rust says, I have a notion of a generic lifetime. I know this is the generic lifetime, and it must be more than this lifetime. This lifetime must be more than this other lifetime. That's how Rust thinks about things. And because Rust thinks about things like that, we don't have to tell Rust what lines our lifetimes are, right? But now we get into the whole method of like modeling this, and this is somewhat complex. So we have this let x equals 5. We're binding x here. We're saying the borrowed value didn't live long enough. They're just showing you a lifetime error here. This is the way Rust thinks about it. Now, before we saw types implemented with generics, right? And we used capital letters for them. Usually single capital letters. X, T, U, V, that kind of stuff. Now we're looking at lifetime arguments, which are always designated with an apostrophe and a lowercase letter by convention. And we say them as in tick A, tick B, tick C, that kind of thing. So when we think of lifetimes, we think of them like that. Now, here's the thing. Every reference has a lifetime. There are rules that Rust has to hide you from that sometimes, and we're going to get to those. But now we're going to see what they look like to have explicit lifetime arguments. A lot of your code won't be using this when you start off. As you get better with generics and you start to understand them better, you get into this lifetime generic stuff, you wrap your head around it, you will then start to use it. But it is totally normal not to rely on this functionality all that heavily when you're a novice, and to try everything to get around it, you know? And in fact, it's actually very controversial whether or not this should even be presented to beginners. There is one woman, her name is Maria Boss, I think, and she has made a very big deal to pull this out of the curriculum entirely, right? And her reasoning is that you can do everything you can do in Python better than you can do it in Python without ever learning this. Therefore, we shouldn't push this on people that are learning the language. And that's a very valid argument. So there's a lot of reason to push this back. But it's in the book, so we're going to cover it. Let x equals 5, let r equals the reference to x, and then we have print. And we are seeing here that we have this thing we can kind of think of as tick B, right? We know that tick B must live at least as long as tick A, right? And we know that tick A must live until here, after the print statement. So we are showing you how we can kind of think about these lifetimes, right? So the data in X must live as long as tick B. We know tick B must live at least as long as tick A, and then the rest is here. Now in main, we don't actually write these lifetimes. Like I said, Rust thinks about this, but we don't think about this. And when we generate code that's invalid, Rust comes back and it tells you, hey, you didn't think about this, you didn't write me any of this, but I can tell you right now this will not work. Because Rust is always thinking about this, whether or not you give it that information or not. You know, and that's nice. Okay, so we have this string 1 is a string from ABCD, and a string 2 is XYZ. And I'm taking result and I'm saying the longest of these two. String 1 as string 2. And I say the longest string is whatever. Now I'm going to show you an implementation of longest, and keep in mind, this implementation doesn't work because we have the pissed off crab. Right? The pissed off crab is on the right-hand side, and it has the question mark next to it. By the way, bonus point, who here knows the crab's name?
Krusty.
No, that'd be a horrible name. How are we going to make the language popular if it's Krusty the Crab? That's the second worst name I could think of, you know. I won't leave out the first one. What?
Rusty.
No, Rusty also not cute, but no. Ferris is his name.
Ferris. Oh,
Yeah.
Birds.
Oh yeah, that's all.
Ferris?
Yeah, that's the name.
Birds.
All right, you know, it is kind of funny because I come from Perl, and I have to admit, like, I don't really get the whole language marketing thing, but they do happen to emerge, and they're somewhat gender balanced these days. You know, like I think the crab is that's a friendly crab. It tends to appeal to men and women, and it's not hyper masculine. Does anyone here know what the symbols are for Perl? Does anyone even know it? This is hilarious to me. A fucking onion and a camel. Like I couldn't imagine two more seemingly, yeah. Anyway, yeah. So I've never, I've only met two programmers, pro programmers that were women. Yeah. I'm not saying it makes all the difference in the world, but it definitely makes a substantial difference when you have cute crabs. Yeah, the onion to me was hilarious. So we have longest. By the way, I may have actually brought them here. Hold on. I bought stickers at some point. I don't know if I have them with me. I do have some stickers. Here, I got coffee stickers. If anyone wants to pass those around. Yeah. I had actually Linux stickers though.
I thought you said Snickers.
No, that's even better. No, I didn't bring Snickers.
You didn't get pizza, so you pulled out the Snickers.
Not just that I not get pizza.
Pizza.
Not just that I not get pizza. Did you see what those bastards did to me?
You just chose not to eat it.
Oh no, I didn't get pizza. I got misery pie. That's what I got. Does anyone here like pineapple pizza? Raise your hand if you suck. Oh man, this is horrible.
Happy to suck.
It's unfortunate.
I just have more options than you, that's all.
Yeah.
You got pizza. That's true.
All right.
Didn't have pineapple on it, though.
Yeah, there you go. You saved me that shit. I appreciate the love. So we have this function longest, and it takes two different string slices, and it returns a string slice. It's looking at x.length and y.length. And if x.length is larger than y.length, it's going to return x. Otherwise, it's going to return y. Why doesn't this work? It doesn't work because there is no reason to assume that x and y will live as long as each other, right? So it doesn't know how to make sense out of the lifetimes in this one, right? Let's say, for instance, you have x.string that lives longer than y.string. Rather, x lives longer than y. And you return y. You would need the result to be y, because the result needs to live at least as long as y in that case. If x is longer, then you're going to return x. And then you need the result to live at least as long as x. So now you're in a situation where you have to know which one of those is longer to determine how long that thing should live. And Rust gets to an area where it says, this doesn't work. Why? Because you need me to figure this out, and you're not telling me this. And the solution here, one of the possible solutions, is this. And what we're doing here is we're saying longest of tick A. Now I'm saying x and y live the same. They must live at least as long as each other. And the last string is going to return to the same lifetime. So that means that it resolves it. You've given a lifetime parameter for both the inputs and the outputs.
Could you also just implement copy? Just copy the...
Could you do what now?
Could you just implement copy and just, instead of passing a reference, just pass a fat copy, return the copy?
No. You know why?
No.
Think about it. What is the return type there?
Well, I can't see the code.
Speak louder. So let's actually talk about this. The question was, what if you, first thing, Rust doesn't have a notion of copying a string slice. It has the notion of cloning a string slice, right? So let's say that you clone the string slice. Why wouldn't that work? It wouldn't work because of this. This is not set to return an owned string. So you have to still functionally answer, if I clone it, who's going to clean it up? Right? You're returning a reference to it. You're returning a string slice. So something is going to have to clean it up. And the problem with cloning it is, when that function is done, it's going to clean up that data. And that slice is no longer going to be valid. So if you want to clone it, you don't return a string slice. You just return a string. Exactly. 100%. 100%. Does that make sense to everyone? Why that question is valid, but the answer, it won't work that way. OK. So here we're saying now we have this tick A, and we're returning the same lifetime. And it tells us that for some lifetime tick A, the function takes 2 type parameters, both of which are string slices that leave at least as long as the lifetime tick A. The function signature also tells Rust that the string slice returned from the function will live at least as the lifetime tick A. So whatever it is for the input, we're saying it has to satisfy both arguments in the output. Cool. And they're showing us an example of it, which is fine. OK, so now this code doesn't work. And why doesn't this code work? So we have this string 1, and we're saying string from, long string is long. Now we're getting into the area where this is stuff that we intuitively know shouldn't work, and we're finding out why it doesn't work, right? So that's what I would call this. This is explaining to you, showing you how the secret sauce functions under the hood. We have this string 1 equals string from, long string is long, and then we have result, and then we have string 2, we're creating this other string, and then we're assigning result to the longest. String 1 is string, string 2 is string. The problem with this, does anyone want to explain it before I explain it? Anyone want to give this a shot?
Well,
No?
I think string 2 goes out of scope. Not sure I understand how exactly.
This is how.
Right, yeah, right.
Right.
Where you're highlighting it just now.
Right. So the problem is that result up here will live longer than the lifetime of string 2. So if longest returns string 2, if string 2 happens to be longer than string 1, it will return string 2. And string 2 cannot live long enough to satisfy being stored in result. It will go out of scope. And the second this scope is over, string 2 is gone, and now result owns a reference to a variable that has already been cleaned up.
So you just have to clone it.
So you have to what?
So you just have to clone it.
Yeah, this is the answer for everything. Still won't work. But that is definitely the easy way to solve this problem. The easy way to solve this problem is to say, I just want to take own types and return own types. Then you can solve this problem, you know? You don't have to worry about things that go out of scope and get cleaned up and how Rust is going to protect you from that. And you'll eventually learn this stuff anyway. It'll seep in slowly, you know? It'll be like a dripping effect rather than you having to learn it before you move to the next step. That's the theory anyway. So we cargo run it, and we get told here, borrowed value does not live as long, right? So this is the problem. Borrowed value used here. So where we're using it is, whoops, we're using it right here, and they're telling us that it doesn't live long enough to be used there because it's going out of scope. Okay, thinking in terms of lifetimes. So this is what I've been trying to communicate, I think, to different levels of success, that there is a method in which you can read just type signatures and lifetimes and understand a lot of the functionality. So here we're reading a function. It's called longest. It is typed to tick A, and we're taking a string slice typed to tick A, another string slice, and we are returning a slice typed to tick A. So what do we know immediately from this, right? We know that this thing here isn't being returned. We're returning a string slice, but it's not based on this because the lifetime is based on this. So we know that we are returning a piece of this. That's one thing we know, right? And right off the bat, what's one thing that would do that? Find the longest substring. That would do that. So if I said, find the longest substring that matches the second argument in the first argument, this is called the needle in the haystack. That's how programmers describe it. We're finding this needle in this haystack. We're returning the location in the haystack. This is what we're looking for. So when we find it in here, we're going to return a piece of that. We're going to return the location in the haystack where the needle is. That's one way you could think about that. That would explain this functionality, and I haven't even seen the implementation of it. Okay. And here's an example. We have this function called longest, and we are taking tick A, and we have x of string, y of string, and we're returning it to a lifetime of tick A, and we say really long string. And the problem here is, in order to make sense of the output, tick A, right, we have to say which one of the inputs it mirrors. Otherwise, we're just creating a new lifetime. And if Rust could solve all of its problems by creating new lifetimes, there would be no problem. Because Rust can always create more lifetimes. That doesn't solve the problem. The point is, when we have these lifetimes, it's to say, this thing I'm returning is tied to one of the two lifetimes here. When I clean up this guy, this is no longer valid. When I clean up this guy, this is no longer valid. These are the hypothetical things that lifetimes are communicating, right? And the reason for that is pretty simple. If I have a string slice and it has a book in it, and I want to return the second chapter, then I can't return the second chapter and then delete the book. That doesn't make sense. I have a location now in memory, and there's no text behind it. There's no book anymore. So you need to say which one of these two this is coming from. That's what Rust is trying to learn from you.
Scroll up a little bit. Farther. That one. Yeah. So what would happen if you defined the longest function in terms of, well, the top one? What would happen if you defined the longest function with x and y being of tick A, even though you're not returning y? I'm assuming you just wouldn't free y.
X and y of tick A. It would work fine so long as you gave them both something of the same lifetime, or something that could ensure that both of those lived at least as long as one of those lifetimes. So you're speaking of, if you define x and y in terms of tick A, you could be doing two things. You could be giving it the same variable for both arguments, totally fine, that would work. Or you could be giving it two different variables that have the same lifetime. They're in the same scope. That would also work, right?
So you're not setting the lifetime, you're just declaring what it needs to be when you pass it.
That is a very valid point. He said you're not setting the lifetime, you're declaring what the lifetime must be when you pass it. That tells me a click to you. Lifetimes in Rust are not prescriptive. Rust isn't asking you to tell it what to do. Rust is making sure that what you're wanting to do can be done, right? Rust already knows what can and can't be done. It wants you to make sure your intentions are the same thing that it's going to do. They are descriptive. You are describing things. You'll never do a lifetime wrong and come up with invalid code, right? Okay. The struct has a single field part that holds a string slice. There we go. Okay, so we are now looking at, I think, the last one we did, which is that, right? So we have this, no? Maybe we're looking at that implementation right above it. Yeah, I think we're looking at this, longest, and now we're coming down here, and we have important excerpt. Okay, let's just, I guess it's a whole new thing. So now we have a struct, and the struct has a lifetime of tick A in part, right? This is true. Anything that stores a reference has to have a lifetime, whether implicit or explicit, because a reference means the data isn't owned. And anytime you see data that isn't owned, you have to have a notion for how long that data is good for. That's where the lifetime system comes into play. So now we have a struct called important excerpt, and this is storing a tick A lifetime. It's over a lifetime of tick A, and I'm saying part is that lifetime. So part is a string, it's going to live that long. So now I come down here. Damn it. Oh, hold on. There, no, lifetime, there we go. Important excerpt, okay. So now the novel is being specified above, right? Called me Ishmael some years ago. This is what I said, the book is in memory. And then I'm saying the first sentence is, and I really like this, again, we have this novel, and novel is you're calling split on a dot, right? Which is gonna return a list of things you can iterate on, right? And we're calling next on it, so that's how I knew that. And then I'm saying except, if you don't have any dots, then you're just gonna die. And then we say let I equals important excerpt, and we're going to say the part is the first sentence. So now the struct is storing a reference to that part of that novel. And it has to live at least as long as the novel. Okay? Okay. So this is fun. This is the part where we get into talking about why we never had to bother with this stuff before. We have talked about references since the first day of class, and we never had to bother with any of this. The question should be, why are we just now seeing it? And this is what I will say. This is very complex. You're just now getting introduced to it. We're on the 10th chapter. You probably will not be using this all that much, and that is because there are very simple rules that make it to where you don't have to encounter this part of Rust that often. Not to say you'll never have to encounter it. This is an absolute must-learn for even intermediate level Rust. But there are 3 simple rules, which are called the elision rules. And the elision rules are things that save you from ever having to write this. And we're going to talk about those now. Okay, they don't actually layer out like I would expect in 1, 2, and 3. I don't want to read all of this. I just want to find the 3 rules.
The first rule is the compiler.
Lifetimes on functions or method parameters are called input lifetimes, and lifetimes are called output. Okay, yada, yada, yada. Here we go. There we go. Okay, so there's the first rule. The first rule is that the compiler assigns a lifetime parameter to each parameter that's a reference. In other words, a function with 1 parameter gets 1 lifetime parameter. So anytime you see that foo function declared right there? Let's make it a little bit bigger. Hope I don't lose it. There we go. And let's get rid of this sidebar. There we go. Okay, let's actually start here. The compiler uses 3 rules to figure out the lifetime of references when they aren't explicit annotations. The first rule applies to input lifetimes, and the second and third rule apply to output lifetimes. If the compiler gets to the end of the 3 rules and there are still references for which it can't figure out lifetimes, the compiler will stop with an error. These rules apply to function definitions as well as impl blocks. The first rule is that the compiler assigns a lifetime parameter to each parameter that's a reference. In other words, a function with 1 parameter gets 1 lifetime parameter. And then we have it defined right here. The function foo over tick A takes an x, which is lifetime tick A of I32. A function with 2 parameters gets 2 separate lifetime parameters. This should be a function with 2 referenced parameters gets 2 separate lifetime parameters. Fn of foo tick A, tick B takes an x, which is of tick A, and a y, which is of tick B, and so on. Okay, so what they're saying here is one of the things that we'll try to do in order to make sense of things, rather than to assume all of the different input parameters have the same lifetime, it will give a different lifetime parameter to each one of them. If you have 10 different references, it'll generate 10 different lifetimes and assign them in sequence to all of those parameters. So you'll have 10 different ones to each one. We'll not make assumptions that any 2 of them are the same. This is the most liberal way to write that lifetime code, right? You could tell the compiler you can be more conservative than that. These are going to be of the same lifetime. Or you can tell it they don't have to be of the same lifetime. Go make it work if you can. And that's the default behavior. The second rule is that if there's exactly 1 input lifetime parameter, that lifetime is assigned to all output lifetime parameters, right? So if you have this tick A of I32, and you're returning an I32, then we automatically know what that return value is going to be. Why? Because you're returning a reference, and in order to return a reference, you have to have a reference, right? You can't create something you own and return a reference to it. It'll go away. So if you're returning a reference, you must have received something by reference. So it says that the thing you're returning must be to the same lifetime of the one thing you received. Second rule. Third rule is that if there are multiple input lifetime parameters, but one of them is self or mute self, because this is a method, the lifetime of self is assigned to all output lifetime parameters. The third rule makes methods much nicer to read and write because fewer symbols are necessary. Okay, the third method is one we can easily create a violation of, right? You have this thing called self that you can accept a reference to in a method. Some methods don't take, most methods in Rust will not take self. The only method in Rust that will take self and not return anything is destroy. You know? If a method in Rust takes self, then you have to, when you get that self back, save it somewhere. Otherwise, the object goes away. So most methods in Rust take a reference to self or a reference to mute self. And what they're telling you here is, if anything in Rust takes a mute self or a reference to self, you can assume the output needs to live as long as the object. True 99% of the time. What if you have a method and it takes a reference to the novel and it's returning a part of that? Well, then you want it typed not to self, but to the novel, because you're not returning anything that you're storing the state on. You have written a very bad method, but it's very easy to violate that, right? So I'm saying that oftentimes it'll make assumptions that work, but there'll be some times where they won't. These are violations of the elision rules, which are just assumptions, and you'll just have to come in and then type it. You know, it's not a big problem. And the compiler will even tell you, this doesn't work this way. You know, how do I know that the type you're receiving, novel, is going to live as long as the object? It'll say, what? It's not. And then it'll say down there, if it's not going to live as long as the object, you need to type out everything, including the object. This is what you have to copy and paste to do it. Rust will tell you that kind of stuff. So I don't think we need to go through all of these. I think the point that I would draw home is that those three rules create a system in which, in very many cases, you don't have to write lifetimes at all. You know, that's the kicker there. These are the rules in which Rust looks a lot cleaner than it may otherwise look because it has simplification rules, you know? And when we're demonstrating Rust, we only ever use things that follow our own simplification rules. We leave the other pieces out. Yeah. Lifetime annotations and method definitions. OK, so now we have a method level, and it takes a reference to self, and it's returning an I32. And we have this impl over tick A, and it's over important excerpt of tick A, right? So we're saying create an implementation over important excerpt of tick A, and it has a function level, and I'm taking self, and I'm returning an I32. OK, nothing shocking there. And in fact, because we're returning an I32, OK, it's telling us which, OK, I see what we're doing. And this is probably what they did for the first 20 things above. They're trying to show you, you don't have to write it because of this elision rule. You don't have to write the types because of this elision rule. It's useful, but I don't, if you don't have to write it, you don't have to write it. I don't know why you should care. Because there could be a fourth elision rule someday, and then there'll be even more stuff you don't have to write. That's how Rust is developed. And I remember when a lot of Rust was a lot more terse. The lifetime parameter declaration after impl and its use after the type name are required, but we're not required to annotate the lifetime to the reference to self because of the first elision rule, which is that every type that you get has its own unique reference, has its own unique lifetime, right? Here's an example of where the third elision lifetime rule applies. And in this one down here, we don't have to specify the type of the return value. So notice here, we don't have a return slice. We're not returning a reference. Because we're not returning a reference, and they're talking about what elision rule is saving you from having to write this, it's the first one. Because only the first elision rule applies on the inputs. The other two elision rules apply on the output. Now in this one, we're returning a reference, right? So what is saving us from having to write the lifetime on the return value of this reference? And the answer is self. We are assuming to return the lifetime of self because of the third elision rule. See? Then because one of the parameters is self, the return type gets the lifetime of self. And all lifetimes have been accounted for. Now that may not be right. But in this case, we hope it is. Static lifetime. So here's another good thing. In Rust, there is one lifetime, which is called static, and it can be used to satisfy any lifetime. So the idea here is that there are a class of data in your Rust program that exists from when you start the program until the program is terminated. That data is called static data. And anytime you have static data, you can supply it to anything, and it'll always work. Why? Because nothing ever has to worry about cleaning up static data. It exists until your program ceases to exist. It exists until the end. And because static data never has to be cleaned up, it effectively is the most useful type of data because it can satisfy any lifetime there is. Nothing ever has to worry about it. A reference to static data is good forever.
It's basically a global variable.
Yeah.
Or a global non-variable, because there's no such thing as mutable static in Rust. So this data here is not mutable. This is a constant.
Gotcha.
This is a constant outside of all scopes in C. That's what that would be. What?
Can't create a global library pointer and then dynamically load it from runtime in Rust.
A global library pointer, and then dynamically load it. You can with FFI, but you can't in Rust. You have to declare it as unsafe. Rust has a notion of unsafe that'll handle that, a global mutable pointer. And there's also something called once, which will handle some of this stuff too, in a type-safe way. Once uses interior mutability. This is really geeky stuff though. So longest with an announcement, now I have this x, y, and this and is gonna be, I guess, short for announcement. So x is a string reference, y is a string reference. They're both typed to the lifetime tick A, and is returning t. I'm showing you the type signatures there. I'm showing you what it requires. I know that t has to implement display, and I'm telling you that this third variable must implement display. So this is the longest function from 1021 that returns the longer of two string slices. But now it has an extra parameter named an of generic type t, which can be filled in by any type that implements the display trait as specified by the where clause. The extra parameter will be printed using the display. Okay, so what they're showing you here is that because I am stating that t must implement display right here, I can print it like this, just in println. So that's the method to say I want to use the display trait to print that. Okay, and that's it. Summary. What do you think? How bad was it?
Read that one again.
How bad was it? As bad? I told you it was going to be rough, you know.
I hung on for the first hour.
Hung on for the first hour. I mean, that's true. Like I said, it's honestly, this is the tough one. So this is the second toughest chapter. I don't think there's anything remaining that is this tough, in my opinion. And the reason why this one is this tough is because it is abstract and it is higher ordered. You have to understand what a type is, what a lifetime is, and then you can start to think of things in terms of higher ordered types and higher ordered lifetimes. And they put both of those in the same chapter. This is a tough one. And it's very normal to come back to it. Anyone have any questions on it? Did anyone feel like they actually understood it or have approached an understanding of it? Okay. Some heads nodding. Some people got some things out of it.
Did anybody without a computer science degree get anything out of it? That I don't know.
I mean, I don't have a computer science degree, and I'm leading the class. So I mean, it's certainly possible without a computer science degree. That much I can assure you. But I will tell you, it's not easy. You know, when people say Rust is difficult, this is what they're getting at. And you know, if you come over here and you look at I just go back to my Stack Overflow and hit my name, and then you know, we'll just do like Rust. I'll show you here how long So here, I have 122 questions on it. Let's do newest, and I'll show you my first one, just for humility, right? And my first question on Rust was in 2019. I didn't start using Rust professionally for, you know, I'd say probably 2 years after that. So it took a while, you know.
It's page 3.
Yeah, I mean, I've asked 122
What's on page 1?
page 1 is the newest,
Page 3,
yeah.
last of the page, reverse order. Got it.
Yeah. So I mean, I'm still asking questions. I have my last question on Rust was November 5th, 2023. And there we go. So my last 3 questions on Rust even got downvoted. There we go. 4 of my last 5 questions on Rust were downvoted.
How embarrassing.
I know. People suck. Yeah.
How many of them were closed as duplicates?
Probably a lot, to be honest. I mean, I don't. This one didn't get closed as duplicates. I always like this. You know, they like the answers, but they don't like the question.
It's so
like
dumb. It's like there was value that came out of it, but fuck you for asking.
Yeah. Yeah.
Close, right?
Yeah. I mean, it's just this is the way that Stack Overflow is. Stack Overflow keeps getting more and more hostile by the year. It's really they need to do something about it. Yeah. I mean, these are complex questions. I don't even want to explain this stuff. This is FFI. This is interoperating with language libraries that are not Rust. You know, Rust, Windows API, and cross-platform bindings. But I mean, I'm just saying it's normal to have questions that receive a lot of downvotes and to have answers that get a lot of upvotes for some reason. You know.
They're just going to take away the downvote, just like any other social media. They'll just get rid of the downvote.
Yeah.